Welcome everyone. Myself Vijay from Optimum AI. I'm here to take the topic on generative AI. That I will take around prompt engineering, retrieval argument generation, fine-tuning large language model, generative AI. First, let us go into the prompt engineering. So prompt engineering is nothing but is the instructions which we give to the LLM, and the LLM gives the relevant response. That's what prompt engineering is. For example, you can see here I asked what is AI to an LLM or GPT. It responded to that given question. It is nothing but prompt engineering is nothing but the instructions which you give, the way we give the instructions. There are different processes in prompt engineering. Like first we have to define the task, what we are going to do, like writing article, blog post or something, anything. And then we have to identify the inputs, like what all should be mentioned in that, and write the detailed prompt of it and see the results. If results are not satisfied, then refine the prompt. These are the process of prompt engineering. And in coming to the key components of the prompt engineering, we have to clearly specify what we want and provide a little bit of background of it so that LLM can understand it better. And we have to give some instructions, like I want it to be like in this format, like explanation of it, summarize of it, or give a list of it in the points like that. And then if we need it, we can provide the examples too. And also we can set the limit. If we directly give the prompt directly, it will give some lengthy answers. So if we want to limit that, I want it in 100 words, 200 words, so that we can give that also. There are different techniques in zero prompt engineering. Like in the first one, it is zero shot prompt, where we give the and it gives the results. For example, I'll show you. It's not a phone. Here I given the query, like what is an AI, it gives the results. This is called as zero shot prompt. Coming to the two shot prompt, here we give some examples to the LLM and it gives the result. Let me give that same example. Here I given the instruction called translate the sentence with providing example. Hello, and that means bonjour, and good morning means bonjour. Now translate, how are you? This is the instruction which I give. Like I have given some example, like hello means bonjour and good morning means bonjour. Now LLM will understand it. Oh, he's translating some text. Just given the result. Coming to the next, there are other options too, like chain of thought prompt, where we have to explain it in detail. Like if we are writing an articles or something like that, then we have to explain it. I want to specifically instructions, definitions, and it should be started in this format and like that. I will show it in the code way. This is for zero shot prompt example, where I give the where condiment is, gives the results that condiment is mayonnaise, and it gives the result. This is how it gives the result. And for few shot prompt, here I give this is a few examples which I give. This is awesome, negative. This is bad, negative, positive. And this is how I give the instruction, what a horrible show. For that, it have to give the result. And that's how it is giving the result. Then coming to the chain of thought prompt, this is how I give the prompt. Like I give the question, then I give the detailed information of it and expect the answer. And that's how it is giving the answer here. There are several other ways of prompt engineering, like role-based prompt engineering. You can see it. This is one of the example where role-based prompt engineering shows the role-based prompt engineering. And there is one more method called one-shot prompt, and several others. The challenge is in the prompt engineering is that bias and fairness, like avoiding introducing or reinforcing bias, ensuring the model gives a consistent result around similar prompts, and preventing the prompt from being too tailored, which might limit the generation, and interpreting the response, understanding why the AI generated a particular output. Use case of prompt engineering. It will be generally used for writing an article, bringing and getting some educational contents and advertisements, and then for the customer support and for research and development. Let me go to the code for I have written in different methods like downloading the model, then using the lang chain, and one more method using Hugging Face pipeline. First, we have to install the requirements, install transformers model or get the model. Let me show you. And here I use the Mistral 7B. So we need transformers to use this model, and bits and bytes to convert the model into 4-bit model or 8-bit model, different smaller version of the model, so that it can fit in the given Colab, free version of the Colab. To use the 4-bit models, bigger models, we have to use a connect into GPU. You can select here and accelerator to accelerate the given GPU. And from the first, we need to load the model using the transformers. So like we have to give some auto tokenizers. We need a tokenizers, get tokenizer of the model. We use the tokenizer of the model. And auto model for casual LLM is for text generation. Here I using the Mistral 7B version 0.1 model from Hugging Face. Here I am logging into the Hugging Face face using the API key. Here you have to give the API key like something whatever it is. Then here I define the prompt. Then I tokenize the prompt. I tokenize the prompt so that it will fit into it will be readable to the LLM. Here the model is the one which I mentioned here, and device map auto. That means whatever the hardware has, use that. Either you can use the -1 or 0 here. Depends. -1 means CPU, I think so, or 0 is something like GPU. If you specify auto, it will do it automatically. I call the tokenizer, and here I tokenize that given prompt, and here I define the GPU. Here I load the model and get the model. Here you can see it. And here also I mentioned the model which I mentioned, and device map is auto, that is for GPU. And here I have given the instruction called load in 4-bit is equal to true. That means it has to get the 4-bit model, means quantize the model and use it. Else the Mistral 7 billion model will be around 16 to 17 GB. Right now I'm using 4 to 5 GB. Then I give the tokenized prompt. I send it to the LLM and generate it, and give the max new token is equal to 200, so that results will be of around 200 tokens. I'll show that what is token is. This is one example where I can show the tokens. Here I given the instruction hello world. It is split into 2 tokens according to the right now. This is an example from OpenAI. It is split into 2 tokens and 11 characters. So these 2 tokens will be in the numerical format, and it will be sent into the LLM to generate it. After generating the results, then I decode that and create the response. Coming to the future prompt, I give the prompt as like this. That is few examples, and expecting the third one result for the third one. Then I tokenize this given prompt and generate the result. Here is the result. Also, there you can see that there is one more method above here from transformers import pipeline. You can use that method too. I'll import the pipeline from transformers. I'll give the prompt, and I use the smaller model because the Mistral 7 will not fit into my GPU. So after the getting it, I get the response for using the given model. Here I used the 400 million tokens model. This is a 7 billion model. Also, we can use create the prompt engineering using the code using LangChain method. First, we need to install the LangChain community, import OS, and then we have to import the Hugging Face endpoint. This is to get API key. Like in here, I can show you. Test this and add new secret key. Give the any name, like I have given Hugging Face API token here, and you can paste your API key here. And to use that, copy this Google Colab import and put your secret key here, and you can save that in variable. There is one more method where you can do it using the environment. We have to create .env file in this folder, a file and .env. Then we have to save it like your API key. It will go here. Then you access that and use that. This is how you have to save it in .env file. Should not put any double inverted comma. And using the Hugging Face endpoint, I call the model name, then give the temperature is equal to 0.3. That is variety of the result. The lesser it will be, the more variety. And here I give the API key for the given model and send the prompt and ask to generate the result. And in chain of thought prompt, it is nothing but we give the prompt in detailed way, like given the question and explain the question in step by step and expect the LLM to give the result. These are all the same steps. It will give the result. In open source model, it will give the results with given prompt input as well as the given output. If we give the max token, or the more we give the max token, it will repeat the answer again and again. That's all about the prompt engineering. Next, we'll go to the RAG. In prompt engineering, we have some drawbacks, like it will not give the content from what we expected. Like we ask some private questions, like regarding the data which I stored in my phone and all, which I stored in the Google Drive or something like that. Then it will not answer to that topic. That means that LLMs are trained for general related content. So to overcome that, we are using the retrieval augmented generation. Example, you can see what is my Gmail account username, even though I have logged in, but it did not unable to answer it. So to overcome that, we go to the retrieval augmented generation model. This is the retrieval augmented generation mechanism. First, we retrieve the relevant content which we want to the LLM to respond. Then we clean it so that there will not be any other external characters or some links and all unwanted materials. Then we split them into the chunks, and then we retrieve the relevant content from the vector storage for the given prompt, and we send that to the post retrieval, and then the generator where the LLM will retrieve the content and generate the result. I'll explain it in detail in next. This is the architecture of RAG, where we collect the diverse data like text, PDF, CSVs, images, videos, and all. We pre-process that content so that if we scrape the content from the internet, there may be irrelevant contents like act, hash, or symbols, other special character symbols, or empty lines and all. To remove that, we pre-process that, and then we split them into the chunks. Chunks is nothing but, let me show you. This is the information which it is given, and here I given the option called character splitter, means that it will count the each characters. Whenever 25th, after 25th character, it will be splitting up. So this will be the one chunk, this will be the second chunk, and this will be the third chunk, so on. You can have the different types of chunk splitters, like sentence based, text length based, or paragraph, like, or you can have at the full stop or each spaces and all. After splitting them into chunks, we convert it into the embeddings so that it can be stored in the vector storage. It is nothing but the numerical representation of the given chunk. Each chunk will be represented with the unique numerical representation. There are different ways of doing it: word to vec, stillbird, and other. After converting it to the embeddings, Then we store the metadata like chunks with embeddings and give some ID, unique ID to that, and store it that in vector storage. When user gives the prompt, that is like I given the this is the prompt. When user gives the prompt, the user prompt will be converted into the numerical representation, and it will give us do the semantic search on the vector storage and retrieve the relevant content from it and send it to the argumenter. And argumenter will have some few short forms like examples, like I have mentioned here, or any other role-based prompts. And argumenter will collect these few short forms and retrieve the relevant content from the vector stores, and the retrieved content will be the chunks and its ID, not the embeddings. Embeddings are only to retrieve the content. These chunks are sent to the argument, and this argument is sent it to the LLM by converting them into the tokenizer. Tokenize means converting into the numerical representation where LLM can understand it. And then LLM will generate the output and then be decoded, and user will get the result. Here, this is the external data, where external data can be of many types, like publicly available data, like there are primary data and secondary data. There are two types of data, like publicly available data and statistical methods, surveys, polls, where we do some polls in Facebook or Twitter or something like that. And secondary data are those which are records which are already saved from by the organization or governments. In why we have to do the data preprocessing, because most of the collected data may have unwanted characters. You can see here that is letter A, and these are some of the words, and there may be some empty spaces. To remove them and all, we preprocess the data and clean the text so that it can be better readable, and it may be contain unwanted links. To remove that too. And after preprocessing the data, we split them into the chunks which I mentioned before. And going to the vector database, it is why do we need vector database? Because we can store the unstructured data, like the documents, images, anything, but it can store that in numerical representation and can be searched through the vector storage within easy format. There are different types of vector database like Farsi, Pinecone, Chroma, and these are the different vector database available in the market. Chroma is open source, and some are paid versions. Vector embeddings, where whatever we split them into the data, we have split them into the chunks, we convert into the numerical representation so that we can store that. The main reason for embedding is that we can convert the images, even the images, to the numerical representation. And one more thing, we can there are different model dimensions, like embedding models have different dimensions, like 384, 77, 68, depending upon the model. Then whatever we converted into the embedding, it will be stored in vector storage, and in vector storage it is stored in such a way that it are grouped in a particular way. It is called as vector indexing. Like you can see here in the graphical representation, wolf, dog, cat, and all, they all stored in the one particular locations. Fruits, banana, apples, which are not equal to the animals section, it are stored in different sections. Similarly, if you were here, you can be having some regarding the car. Coming to the vector search is nothing but for the given query, it will find the meaning of that given query and retrieve the content of it. If I give the query as a kitten, it will fetch the relevant meaningful words of that. For example, here I give given the motorcycle. These are the list of them which it give. It will not give the do the keyword search. Instead, it will give the meaning of that word. I can show you that one too. Here I given the word. The given prompt is the mobile. If the user gives the prompt as mobile, this is how the semantic search works, where it will retrieve the not just the keyword word. Instead, it will go through the meaning of that word, and it will fetch the relevant content of it. Like wireless, it is related to the mobile. Portable, it is related to the mobile. iOS is related to the mobile. So like that. And we can also it is somewhat internally it happens some mathematical operations like Euclidean distance method, Manhattan method, cosine similarity, and dot productivity. Now, after searching the query, relevant data from the vector storage, and it is the data is retrieved from the content, then the retrieved data will be re-ranked so that organized in such a way that the topmost you can see here. This is one similar kind of re-ranker where the most nearest one will be the top, will be at the top, and the least nearest will be at the bottom. This is how it is then re-ranked, and the argumenter will be sent it to the LLM with the given prompt, example prompt, and generator will generate the result. We show the example code. I'm using QI PDF reader so that to read the PDF file, can upload the PDF file through here. Go to files, upload. Saved a RAG PDF file from the internet and saved it as RAG. We have to import the PDF reader for reading the PDF, and then we read the PDF on the given path. This is the given path. You can get the path here, and we can just paste that here. And after reading the PDF, we have to iterate through each of the pages and retrieve the text of it. And this is how it is. From page number 1, this is the content which I received. And after that, I split them into the chunks. I using the lang chain to split them into the chunks. Here I'm not doing any data preprocessing part because there's only small PDF, and I'm using the character text editor from the lang chain. And in character text editor, I'm separating it instead for empty space, and chunk size is around 200 for each 200. There is no need of this. Chunk size is 200. That is for each 200 character, it will be one chunk. Like this is saying around 200 characters. And chunk overlap is equal to 20. That means from first chunk to the second chunk, I store that visually. Chunk overlap is nothing but the here in the given first chunk, it will reach up to the 25, and that is important. What will be this is the chunk size of first one, and if I give chunk overlap as 6, then the second chunk will start from the 19th of the given first chunk. So I reduce it to 2, then it will start from here like that. Then I call this text splitter to split the given text, and just to print the text to see it. This is one of the chunk. Then I'm converting to the embeddings using the sentence transformer library, and I'm using the all mini LM model to transform the given chunk into the embeddings. It is nothing but the encoding the given chunk. After converting it to the embeddings, I store them. To store that, I use ChromaDB, which is an open source model. Where we have to install the pip install ChromaDB. Then we have to call its client. Then we have to create the collection called new collection. That is where we store the our content. Can give the different name here. Here I store the content in different forms. Like for that given embeddings, I will store its ID, create the ID, and store its metadata. Metadata is nothing but the chunks you see here. Here I'm just nothing but generating IDs to the each metadata, and just checking it, verifying it if they're equal or not, and then adding that into the ChromaDB. This is my the user gives the prompt. Then I encode that, means convert it to the embedding. And then I do the semantic search for the given query. Like for the given user query, it will collect the retrieve the content of the meaning of the, means it will search the meaning of it and fetch the relevant content. This is how and I have given the end result is equal to 5. That means it will be the 5 top results. Doc 84 will be the nearest one. Doc 95 will be the second nearest one. Like I mentioned here, the list which I shown here. That is nothing but ranker. So it will retrieve these IDs and metadata. Metadata is nothing but the chunks. It will not retrieve the embeddings. Here I load the API key. You can just directly give the API key here, or in a other method is you can try this one too, where you can directly give the key here. Here I'm calling the model. In this RAG concept, I am using the Mistral 7B instruct version 0.1. For that, I need accelerator to use the GPU and bits and bytes so that I can convert into the smaller models like 4-bit, 8-bit, 16. This is similar which I mentioned before, like tokenizer, where I get the tokenizer of the given for the given model and get the 4-bit model. In this code, I downloaded the model and using it. This is nothing but the retrieved content. It has got a lot of unwanted things. So I do a small data pre-processing of that so that only the text, the modular rack, these will be retrieved. So this is how it looks like. And I am using the prompt template from the LangChain. I'm using the future prompt template so that LLM can understand it in a better way. Here I give the examples like what is RAG and its output, and then another input, how does RAG work, and expecting the output. And for that, I give the next input as what is modular RAG and expecting the LLM to give the result. We have to format that is in the prompt template. After formatting the prompt template, we have to send it to the LLM and it will generate the result. I mean, sorry, here we tokenize that given prompt and we generate the result. And I have given max new token as 200. And then we decode that. And here I given me some code so that only the results will be displayed. The above example, what open source does that, it will, for the given question, it will give the print the result prompt as well as the result. So to overcome that, I use a small code so to filter out and print only the result. RAG can be used in different applications like advanced question answering for the content creations, legal analysis, like for the law-based question and answering, text completion and translation for the customer support of the particular company or anything. I will share this code, the prompt engineering code and copy of RAG. You can try it out in your system. First, you have to create an account in Hugging Face and go to the create an API key, and we can save it somewhere else. Either you can store it here, or you can just paste it in here. You can do it in different way. You can choose in one of the method. That's it for today. Tomorrow we'll cover fine tuning models and generative AI frameworks.